All right, welcome. We're going to talk through some of the questions. We're going to talk through 2018 problem number 3. This is a mix of topics. There's some Unit 4 stuff in there. There's also some things from earlier units. And please do make sure you try this problem first before watching this video. So do your best. The whole process of attempting it on your own is what really solidifies our learning here. And these AP release problems are challenging, and the reason why we do them is just to help practice our problem solving skills and to try and apply our knowledge to new situations. And I encourage you to talk through these questions with someone else as you're going through it the first time too, so you can get ideas of different problem solving strategies different people might have. All right, so this first part of the question says write the ground state electron configuration. So I'm going to write the electron configuration. I'm looking at my periodic table. Remember, we have that pattern where that filling order we've talked about, where this over here is the S block, this over here is the P block, this over here is the D block. And remember, for the S and P, the row number matches what shell they're in. And then for the D block, it's one behind. So like this section right here, for example, is filling up the 3D. Okay. And it's asking me for the electron configuration of the iron ion. And usually what I might recommend doing when you're looking at an ion is to write the neutral version first before you try and figure out what the ion is. So let's write the neutral version. So iron is 1s2, 2s2, 2p6, 3s2. You see I'm just kind of working my way across this periodic table. I'm following my pattern. Now I'm right here. Next is 3p6. And then, whoops, go back there. And then 4s2. And then iron is 1, 2, 3, 4, 5, 6 in on the D block. And so now I want to look at, that's just neutral iron. Now I want to look at the iron ion. And so when you form a cation, you're going to lose your valence electrons. So my valence electrons are the ones in the highest energy level. So that's these ones. So my electron configuration looks like this. I'm going to rewrite it without that 4s. If I could also write it as a noble gas shortcut. So I could say that iron plus 2 is like argon with some electrons in the 3d6. You might see here why it's helpful that I wrote out the original neutral version of iron first. Rather than just saying, oh, +2, it's got +2 charge, that just means it has 2 fewer electrons, because that's not actually how it works. So the iron with the +2 charge does not look like chromium, because the electrons it's losing are from the 4s and not the 3d. So that's the benefit of writing out the neutral version first. You can double check and say, who are my valence electrons? Which electrons am I really going to lose in this situation? All right, look at B. We have the radii of these two ions, and we're asked to explain why the iron ion is larger than the iron +3 ion. So this is the iron, so I need to think about what the iron +3 ion looks like. So this is the iron +2 ion. If I were to form the iron +3 ion, then I have to lose 3 electrons. So the first 2 are going to be from the 4s, and then the rest are going to be from the 3d. So it's going to lose 2 from the 4s and 1 from the 3d. So if you look at these two ions, they both have the same nuclear charge, right? So they both have 26 protons in their nucleus. And they both have the same number of shells. They both have 3 shells there. So let's focus on what's different. Well, the only difference in this is that the iron +2 ion has more electrons, right? It's got 1 more electron than the iron +3 ion. And what we know about electrons is electrons are negative and they are going to repel each other. So because they have the same number of protons, they have the same number of shells, the only difference here is the number of electrons. What we'll notice is that since iron +2 has more electrons, it's going to have a little more repulsion in that 3D subshell, and so its electrons are going to spread out a little more. That's why it has a larger radius. So those adding in negative electrons repel each other and makes them spread out due to that, in this type of question, you should look at the scoring guidelines as well as I'm talking through this, but you want to mention the electron repulsion. That's something that should pop up in your explanation there. And then C is, let's imagine that you dissolve these ions in water. So you've got the iron +2 ion, and you've got the iron +3 ion. If you imagine what would happen when you put them in water, we know water's polar. So the negative side of water is going to attract these positive ions. We call that an ion dipole attraction. Sorry about that. You don't have to mention that here, but just FYI, it's an ion dipole IMF they're experiencing. And it looks like this ion has a stronger attraction than this one over here. And we want to justify why that is using Coulomb's law. So with Coulomb's law, we know that the attractive force is proportional to the charge over the distance. And so there's two arguments you could go with here. You could say, one, the +3 ion is more attracted because it has a larger charge. So it's a +3 charge as opposed to a +2 charge. Also, you can look at the ionic radius and say that iron +3 ion has a smaller radius than the +2 ion. You might remember these arguments thinking back to ionic bonding and lattice energy, right? So ions with higher charges and or smaller radii are more strongly attracted to each other. So that's what we're observing here, except in this case, we're just thinking about the attraction to water instead of the attraction to another ion. But it's the same principle of attraction here. So the iron +3 ion, it's got a higher charge and it's got a smaller size. You can mention either one of those things to earn credit for this one. All right, so you see how we're sticking with the theme of iron, but now we've got a redox reaction and a titration happening. So totally different topic here. We've got this, we got a titration of iron +2 with permanganate. We did a somewhat similar titration lab. We titrated hydrogen peroxide with permanganate. And the first question says, write the balanced equation for the half reaction for the oxidation of iron +2 to iron +3. So I'm going to look at these two right here. So iron +2 going to iron +3. So let me write that out. +2 is my reactant, +3 is my product, and it is being oxidized. Where oxidized means it's losing electrons, and I can see that because the charge is becoming more positive. So I'm going to ask myself, how many electrons is this iron losing? Well, it looks like it is losing 1 electron. So I could write it like that. So it looks like each iron is losing 1 electron. And you can put a 1 in front of it if you want, or not. Whoa. Okay. You might notice that in this reaction, there's a 5 in front of it. So what that means is in total, there were 5 irons. And so in total, there were 5 electrons being lost. But if I'm focusing just on the half reaction, I can simplify that and kind of get rid of the 5s and just write it this way. So that's what we call the half reaction. So in these half reactions, that oxidation half reactions have electrons on the right side. That's because they're giving up electrons. If we were to look at a reduction, it would have electrons on the left side because it'd be gaining electrons. The second one, I didn't leave myself much room here. So the iron, I need to do a titration. So I have remember a titration is a problem-solving strategy for figuring out the concentration of an unknown. So I need to do a little stoichiometry here. I might pause for a moment and give myself some more space. Okay, here we go. So just a reminder of what a titration is, just so we can refresh our memory of what we do. Typically, we have our unknown down here in a flask, and then in a burette, we have our solution with a known concentration. In this lab, it looks like our known is the potassium permanganate, and we know that it's a 0.035 molar solution. And when we do the titration, what we're trying to do is figure out how much, like what volume of this solution it takes to react everything that's down here in the flask. So what's down here in the flask? We've got 10 mil of this iron +2 solution, and the concentration is our unknown. And then we've got our balanced chemical equation. This tells us how these two substances react, because without a chemical equation, we can't do much with this information. So the chemical equation tells us that for every 5 irons, you need 1 permanganate for every 5 irons. So let me write down this mole ratio. So we need 1 permanganate for every 5 iron ions. So this is a stoichiometry problem. And whenever you're doing a stoichiometry problem, you're starting with your known, you're trying to figure out an unknown. First step is always find moles. So first step, I'm going to find moles of my known. So this is a solution. So with solutions, we measure the concentration using molarity. So the molarity is the moles per liter. So to find out my moles of KMNO4, I'm going to take my molarity times my liters. That'll give me my moles. So my molarity is 0.035. And then my liters, I got to make sure I convert this value into liters. And then let me stop and check my calculation here. This would be 0.123612 moles of KMNO4. Careful about dropping zeros. This is something I've noticed several people do, is when they're transferring numbers down maybe from their calculator, they accidentally leave a 0 off, and then that can just throw off everything else. So be careful with that. So that's your moles of KMNO4. Once you know moles of your known, then you're going to use your mole ratio. So that's 0.0612, and that's KMNO4. Notice this answer is going to have 3 sig figs in it, because my molarity had 3 sig figs, my volume had 4. So this is going to have 3 sig figs in it. And then now I'm going to use my mole ratio. So for every 1 KMNO4, we react 5 irons. So the iron's going to be 5 times as much there. So we got 1, 2, 3, 0, 6 moles of iron. And then our last step is to find the molarity of the iron. So molarity is moles per liter. And remember, the molarity is defined on your equation sheet. It's written out in a sentence, though. It's a little weird. It says, this sentence says molarity is moles of solute per liter of solution. So it's not written like an equation, but it's written out as a sentence. So anyways, I'm going to take my moles of iron and then divide it by my volume of iron. Make sure you use the right volume. So I'm going to use this volume. That's the solution I'm trying to find the molarity of. And then this is my molarity of the iron. It's 0.306 molar iron. All right, next question. This is kind of experimental technique, trying to assess, maybe have you done a titration before? Are you familiar with glassware? So if we think back to these pieces of glassware, the burette is the thing that we typically use in a titration that holds our known solution, a graduated cylinder, a beaker, and a volumetric flask. So the question says, if you want to measure out 10 mils of iron plus 2, you have to choose between this glassware. And the question actually doesn't ask you to say which glassware is best. It actually says, explain why the 25 mil volumetric flask would be a bad choice. So why would you not want to use that one? If you want to remember what the 25 mil volumetric looks like, we might not have used that size specifically, but the volumetric flasks look like this. And they have just one marking on them. They only have one measurement. And so if it is a 25 mil volumetric flask, that means there's only one mark on it. It measures 25 mils exactly. So it's great if you want to make a 25 mil solution, but it's pretty much useless if you want to measure out anything else. So if you want 10 mils of iron plus 2, there's no markings on here that tell you where 10 mils are. So this is not a good choice. A burette or a graduated cylinder would be much better choices. Beakers are also not great measuring devices. They're not very accurate. So of these, the burette is typically going to be your most accurate. You don't have to discuss this in the question, but just as an FYI. And then graduated cylinders are pretty good. Beakers, you should never use a beaker to actually measure something. Beakers are just for holding stuff. All right, so now let's take a look at these ones. So we've got a reaction. We've got some iron that is reacting with some oxygen to make iron oxide. So it looks like we can maybe write out a balanced chemical equation if we wanted to. Looks like this reaction is happening. And you don't actually have to write this reaction out, but I was just doing that so you could see what's happening there. So iron's reacting with oxygen to make your iron oxide. And you want to calculate the number of moles of iron in the iron oxide produced. So Notice that this data table gives us a mass of iron oxide. And so what we're trying to do here is, trying to find my calculator here, so what we know for G is we know that we have 7.531 grams of iron oxide. And we're trying to figure out moles of Fe. And there's a couple different ways you can solve this, but one thing that you can do is you can convert this into moles. So we can say that we know grams of iron oxide, we can figure out what the molar mass of iron oxide is. Look at the periodic table. That's 159.7. And so that's 0.04716 moles of iron oxide. But I want to figure out the moles of just iron. So we can see that for every 1 iron oxide, you have 2 iron atoms in there. So the amount of iron is going to be double your amount of iron oxide. And that's 0.09431. That's your moles of iron. So that's it for G. Another strategy, if you're interested, and I posted this in the scoring guidelines you could check, you could also use mass percent. You could figure out the mass percent of iron in iron oxide, and from there determine how many grams of iron you had and convert grams of iron to moles of iron. So that would also work there. And then for H, you want to find the percent by mass of iron in the original sample. So this is actually kind of similar to the brass lab we did, where we tried to figure out the mass percent of copper in the original brass. So remember, if you're trying to find a mass percent, it's just any percent in general. It's the part over the whole. So we're trying to find the mass percent of iron in the original sample. You want to do the mass of iron divided by the mass of the original sample. And so to find the mass of iron, you would use your moles. You'd say I got 0.09431 moles of iron. By the way, if you did the G wrong and you got like the wrong answer here, as long as you use that answer correctly in part H, you would still earn full credit. So it's always important to, even if you're not sure how to do a problem, just try something and make a guess, because then you could use your answer later on in other parts of the problem, and you might be able to earn credit later on, even if maybe you made a mistake here. So don't leave something blank. Give it a shot, make a guess. I can help you out in the long run. So anyways, I found my grams of iron. That ends up being 5.267, plug it in your calculator, and then divide by the mass of the entire sample, which is right up here from the data table. And then when you do that, you should end up with 78.3%. I should have 4 sig figs there. All right. And then that last question with this this percent error one, I find this one is one of the trickier ones I have seen. So don't feel bad if you thought this one was kind of hard to answer for that I. The question is, if the oxidation was incomplete, right, so that some of the product was actually FeO instead of Fe2O3, would the calculated mass percent be higher, lower, or same as the actual mass percent? Okay, so there is an answer in the scoring guidelines, which you can read, and maybe you'll find that clarifying, or maybe you'll still be thinking, what are they talking about? So let's talk about this one. I'm going to erase these real quick so I have room to write. So the question is, like, we are assuming that all of our product is Fe2O3, right? And the question is, what if we actually made some FeO? So let's consider those two things. So Fe2O3 or FeO. Turns out one of the useful things to think about is, what is the mass percent of iron in these two compounds? So if you were to figure out the mass percent of iron in these two compounds, you take the mass of the iron. It's a nice little review of mass percent. So you've got 2 irons, and then divide it by the mass of the whole thing, which would be 2 irons and 3 oxygens. So that's how mass percent works, multiplied by 100. So iron oxide is 70% iron by mass. If you do that same calculation for just FeO, we'll find that it is 77% iron by mass. So if you assume that your product is 70% iron, but it actually is 77% iron, you're going to underestimate the amount of iron in your sample. Okay, so let's give an example. So if you make 1 gram, if you collect 1 gram of a sample, and you're assuming that it's all Fe2O3, you're going to think, oh, I had 0.7 grams of iron in my original impurity. But in reality, if you were, let's say, what the question is saying is, what if you actually made FeO instead of Fe2O3? So let's say you made 1 gram of FeO, then that would actually mean you had 0.77 grams of iron. So what that would mean is you would be thinking it's Fe2O3, so you'd be thinking you only had 0.7 grams, but in reality, maybe you made FeO, so you actually had more grams of iron. So the correct answer is you would actually underestimate the mass percent of iron, because you would think there's less iron in there than there actually was, because you're thinking you made iron, you know, Fe2O3. In reality, maybe you made some FeO. So again, this is this requires some thinking through for sure. So don't feel bad if you thought this one was a tricky error analysis. I think personally it's one of the trickier ones. All right, so hopefully that helps. You know, just email me with other questions too.